right, looking at the first one. Again, today practicing more with exponential and log equations. Is the first one an exponential or a log equation? Log, how do we know? It says log in it, good.
That's why
log equations, we learned how to do this last week on the block day. We couldn't solve a log equation unless we just had one log all by itself isolated. And right now we have two logs, but we have a way to make those two logs one log. What is it? It is something property, more specific though.
And then we call it quotient property.
Quotient property. We're going to condense using the quotient property, which, yes, does turn into division. So we're going to... You would have known how to do it, yes. So we need to condense first using quotient property. Okay. So when we condense these two, we'll end up with just one log base 2, just one of them, and we'll get a fraction in the argument. What's on the top of the fraction? 2x minus 3. What's on the bottom? X plus 4, and that's going to equal 2. Okay, yay, we have it condensed into just one log. Did that. Now that we have just one log base 2, how do we cancel log base 2? Not multiply it.
Square it.
Not square it. Exponentiate it. Yes. We're going to cancel log base 2 using a big base 2. Cancel log base 2 using a big base 2. Basically, both of these sides are going to become an exponent on a big base of 2. So this 2 will become an exponent on a big base 2. This giant thing will become an exponent on a big base 2. The whole point of doing that on the left side, though, is 2 to the power log base 2 does what? Cancels. And we're left with just the argument, which is 2x minus 3 over x plus 4. On the right side, I have 2 squared, which is just 4. Very nice. Okay. Now it's just kind of like a regular-looking equation, kind of a regular-looking equation. What y'all want to do? Multiply by what? Yeah, multiply by that denominator of x plus 4, and that just at least cancels the denominator. Good job. Okay, so that gives me, let's see, I'll have 2x minus 3 on the left side. On the right side, I'll have 4 times that quantity of x plus 4, which we can kind of distribute out. 4 times x would be 4x. 4 times 4 would be 16. All right, very algebra 1 looking equation now. We got to get our variables on one side. Which one y'all want to cancel? Minus 4x, minus 4x. Okay, I'm going to move it up here. So let's see, on the left side, I'll have 2x minus 4x, which is negative 2x minus 3 equals 16. Okay, let's see, canceling that minus 3 by adding, which gives me negative 2x equals 19. Divide both sides by negative 2, and you get x equals negative 19 over 2. All right, so let's think for a second. This was a log equation. Let's see. So we learned how to solve both exponential and log equations last week. Which of these two were ones that we had to check for extraneous answer? Which one? No, we had to check log equations for exponential. Okay, so I need to check this in my original arguments. And I don't want this number to make any of my original arguments negative. Let's check real quick. What is negative 19 over 2? Negative 9.5. So on the first one, if I did 2 times negative 9.5 and then subtracted 3, is that going to make this argument negative? Yes. What does that mean? It's extraneous. It's not going to be defined because the argument of a log can't be negative. Cross that one out. Maybe make yourself a little note. Argument can't be negative. What does that mean then? Yeah, this one has no solution. No solution. The one number we had didn't work. All right, looking at this second one, we did one like this on Friday. Okay, is this an exponential or log equation? Exponential, because the variable's in the exponent. Do y'all remember the first step of this? Cancel one of the logs. Yeah, it's actually easiest to cancel this log because that's less I have to write. I don't have to write log and a little base. So our first step again was to cancel one of these two bases using a log, and we decided to cancel e, so we're going to do ln on both sides, which again is natural log. Okay, so on the left side, that's going to give me natural log of 6 to the power of x minus 13. And on the right, the natural log of e is going to cancel and leave us with 2x minus 1. What did we do after that? This is the step that Mason knew this one. Put the exponent in front. We do the power property, put the exponent in front. X minus 13 times the natural log of 6 equals 2x minus 1. Okay, then what do we do? That is not what we did. Feel free to get your notes out from last time. We did not divide. Huh? Can't do that yet. You can only do that if you have the natural log isolated. I don't have that isolated. Yeah, all right, let's flip back in our notes on Friday. I know we wrote down steps on Friday. Y'all gonna have to be able to do this on Thursday all by yourself with no steps listed. Not dividing. Nope. Again, let's stop guessing and let's get on our notes from Friday where we literally wrote down the steps. Alright, so we started with canceling a base, and then we used the power property. And then now we're on step 3. Huh? Distribute. Thanks, Ben. We've sat here all day. Distribute. Where do we distribute? On the left side. Basically, this natural log of 6, this is just a number. We need to take this number and distribute it. Okay, so we'll have x times the natural log of 6, which we're going to write that up front. X times natural log of 6. And then we'll have negative 13 times natural log of 6 equals 2x minus 1. Okay? Then what did we do? And should have kept those notes out.
Oh, combine like variance.
Yeah, kind of, yeah. We have an equation that has variables on both sides, and we need to get these variables on one side, and we need to get these non-variables on the other side. So get variables on the same side. On the same side. Which one do you want to subtract? Do you want to subtract the 6 ln or x ln 6 or the 2x? So subtract the ones on the left. All right, minus x ln 6 minus x ln 6. So that means we have our x's on the right side, which means what do we not want on the right side? The minus 1. How do I cancel it? Add 1. So we're going to plus 1. All right, let's clean it up. So we're going to have a canceling here, canceling here. So on my left side, I'm going to have negative 13 ln 6. Where does that 1 add to? The caboose, just to the right side. It doesn't add to the negative 13. It doesn't add to your argument. It just becomes plus 1. Equals 2x minus x natural log of 6. Then what did we do? That was step 4. Step 5? Do what? Factor out the x. Yes, on the side with the x's, we don't want 2 x's. We want to get these 2 x's to turn into 1 x, and the only way to do that is to factor out an x. Like a little baby GCF. So we'll get x times, if we divide 2x by x, we get egg, or we get 2, good job. Minus, if we divide x, ln 6 divided by x, we'll get natural log of 6. And then nothing changed over here on the left. Okay, and I have one last step. What's my last step? Isolate x by dividing by this whole parenthesis. Good. Isolate x by dividing by the whole parenthesis on this right side. And then this becomes your exact answer. I'm going to scoot it over here. Okay, so my exact answer is negative 13 times the natural log of 6 plus 1 over 2 minus natural log of 6. Okay. If you wanted to, you could turn that into a decimal. Don't want to do that? We got calculators on the desk. No? Okay. All right. This one's actually not too hard to turn into a decimal because remember there is a natural log button. All right, looking at our third one. The third one, this is actually the first time we've seen one that looks like this. 2 to the power of 2x minus 4 times 2 to the power of x minus 5 equals 0. Okay. Is this an exponential or a log equation? Exponential, right. Okay. So I can't really rewrite everything with the same base. The 2 I could, the 4 I could, the 2 I could, but not this minus 5 here. So we're going to use a brand new method. So what we're going to do is I'm going to start by just kind of rewriting this 2 to the power of 2x, just using my exponent properties. I'm going to write that as 2 to the power of x times 2, which means the same thing. I'm just using exponent properties to write it slightly different. Minus 4 times 2 to the x minus 5 equals 0. Now, if you look through that equation, what do you notice? There's 2 of those 2 to the power of x's now. Yes. Okay, so what I'm going to do... Say it again.
The first one, is it 2 to the power of x times 2 or 2 to the power of x? You said
2 to the power of x squared. All right, so what I'm going to do is we're going to take both of these 2 to the power of x's and we're going to swap them out for a different letter, okay? So I'm going to say we're going to let, everywhere we see a 2 to the power of x, we're going to pick a whole new letter for that. I'm going to call that letter u. We don't want to use x because we already had an x. So in place of this 2 to the power of x, what am I going to put? U. Okay, and then it was squared, so I'm going to put that square on it. So we swap this out for our u. It was squared, and then we have minus 4 in place of this 2 to the power of x. What are we going to put? A u minus 5 equals 0. Now, what does it look like? Yeah, it looks like a regular trinomial polynomial, which we can factor to solve. Specifically easy factoring, where we just need 2 numbers that multiply to negative 5, but they add to negative 4. Definitely a 5 and 1. Which one needs to be negative? The 5, yes. Okay. So I'm going to put those in my parentheses. So one of them will have u minus 5. One of them will have u plus 1. And then are these the 2 answers? No, remember you still got to solve those using your little baby equations. One says u minus 5 equals 0. One says u plus 1 equals 0. So one solution is u equals 5, and the other solution is u equals negative 1. And now remember, that's just what u equals. That's not what the actual variable that we originally needed to solve for equals. So I'm going to come over here and we're going to do a process called back substituting. Basically just putting our u back as what it originally was. Back substitute the u for the 2 to the power of x. Okay, so in place of my u equals -5, I'm going to write 2 to the power of x equals, in place of my u equals 5, I'm going to write 2 to the power of x equals 5. And then in place of my u equals -1, what are we going to write? 2 to the power of x equals -1. Okay, so we have 2 tiny little exponential equations to solve now. Okay, so I have this exponential equation. I have the power isolated, which means we can cancel this base using what? Log base 2, which means I'm going to log base 2 on the right side. So we'll get x equals log base 2 of 5. Okay. On the right-hand side, again, I have the power isolated. I have 2 to the power of x isolated, so I can cancel that big base 2 using a log base 2. So we'll have log base 2 of -1. Does anyone see a problem with either of these answers? Right, the right one has the argument showing as being negative, which is undefined. Logs can't have negative arguments. Well, we are going to cross that one off again because the argument can't be negative. Extraneous argument can't be negative. If you wanted to, you could turn this one into a decimal using change of base. I'm going to have us do that on this one just for the practice. So that would be common log of 5 over common log of 2. We'll grab our calculator, see what that equals. 2.32-ish approximately. Oh, what? Now it's sorry. So we have our exact answer and our decimal approximate. All right, 2 applications on the back. Word problems, science. Anyone still writing? All right, let's look at this science one. Half-life of a radioactive element. What science is this? Sounds very chemistry. Yes. Okay. So looking at this formula, we have A equals A with a little subscript of 0, which I think is read as A naught. And then we have is 1/2 as a base on an exponent. And then in the base, we have T divided by, this is a Greek letter. Anyone know what Greek letter this is?
Theta.
It's lambda. It's lambda. Oh, that one. Yes. All right, let's look through it. Says A is the current amount. A naught, which is the A with the little 0, is the initial amount. T is the time. Lambda is the half-life of the element. And it says the time and the half-life must be in the same unit of time. I'm going to label that lambda. I think that's spelled right. Okay. Suppose that an archaeologist discovers the remains of a campfire at an excavation site. Testing some of the charcoal, she finds that it currently contains 2.4 times 10 to the negative 12 grams of carbon-14. By examining the decay products, mostly nitrogen, remaining in the charcoal, she determines that it initially had 5.2 times 10 to the negative 12 grams of carbon-14. The half-life of carbon-14 is about 5,730 years. Yikes. How old is the campfire? All right, I'm going to underline this. What are we solving for? Which variable? T, yeah, time. Okay, which means we should be given all the other variables. We should be given A naught, and lambda, which is the half-life. All right, starting with our A, our final amount. What would be our final amount? Between these two, which one's final?
0.4 times 10.
Yeah, this one, 2.4 times 10 to the negative 12 equals our A naught, which is our starting amount. That's this one, 5.2 times 10 to the negative 12. And then we have a base of 1/2. And then in our exponent, we're going to have T divided by our half-life. T divided by, what is the half-life? 5,730 years. All right, this is an exponential function because the variable is in the exponent. Okay, so I know eventually I'm going to have to use a log to cancel my base, but it's not isolated yet. We're going to need to isolate this power right here so that we can eventually use a log to cancel that base. Isolate the power. Which Danny said to do that, we're going to have to divide by this 5.2 times 10 to the negative 12, which you can do all at once. It's kind of like all together right here. So we're going to divide by 5.2 times 10 to the negative 2. I think I said 12 earlier, but it's 10 to the negative 2. We'll divide over here as well. Did I write it wrong? Oh, I did. It is a 12. I just wrote it wrong in my problem. Thanks. Okay. On the right side, those two are going to cancel. On the left side, technically part of it does cancel. Which part of it cancels? The 10 and negative 12s cancel, and you really just need to do 2.4 divided by 5.2. What is 2.4 divided by 5.2? Gross. It's an ugly decimal. How do I make it a fraction? Math, frag. Thanks, Sean. 6/13. All right. So this left side here simplified to 6/13 equals 1/2 to the power of T over 5,730. Excellent. Have we isolated the power now? Yes, we have isolated the power, which means now we can use our log to cancel that base. Cancel the base.
Log 1.
Using log with a base of 1/2. Log base 1/2. We're going to log base 1/2 over here on the left as well. Cancel, cancel. Okay. I'm going to scoot my work over on the right. So on the left side of my equation, I still have log base 1/2 of 6/13. On the right side, what do I have now?
T over 5730.
T over 5730. I'm going to write it as a regular looking fraction now instead of a slanted one. Excellent. We got one more step to isolate T. What is it? Multiply by the denominator of this fraction. Times 5730. Where do I multiply that on the left side though? Usually we put multiply in the front, but yes, just not in the base, not in the argument, out front. Times 5730. Okay, so let's see. I'll have 5,730 times log base 1/2 of 6/13, which again is the exact answer. But if this archaeologist was like, how old is that campfire? And you answered with the word log in it, we might think you're a little crazy. We want an actual number. So I'm going to use my change of base rule to be able to do this. So I'm going to have 5730. 5730 times, and then we have two common logs. What's the top common log going to have in its argument? 6/13. What's the bottom one going to have? 1/2. Good. Let's see. 5730 times. I'm going to use my cube fraction for this. Do you remember how to get the cube fraction? You press alpha, and you press y equals on the top left, and then you just select the first option. All right. Then in the numerator, we'll have log of 6 over 13. 6 divided by 13. On the bottom, we're going to have log of 1 over 2. 1 divided by 2. Close both of those. Got it typed right. 5730. Common log looks good. Dang, that's an old campfire. 6,391.7 years. What did you say? 0.7 years. All right, one more. Boys, lift your head. Richter scale. Again, science question. I don't know what science this is. What do y'all think Richter scale is? Physics? Geology. Sounds good. It's used for measuring the magnitude of an earthquake. We've heard of this before, right? After there's a big earthquake, we heard measured a blah, blah, blah on the Richter scale. The Richter magnitude can be calculated using, so R is our Richter magnitude. We've got 2/3 times the log of 0.37 E plus 1.46. Says E is the energy released by the earthquake measured in kilowatt hours. Okay, R is the number on the Richter scale. In February of 1812, an earthquake occurred in New Madrid, Missouri that flattened the town, causing part of the Mississippi River to change course, and according to newspapers at the time, it made church bells ring as far away as Boston and Toronto. Isn't that crazy? And it's in Missouri. I haven't ever heard of earthquakes in Missouri, but it's true. True story. No direct measurements were taken because this was 1812. Since no earthquake stations had yet been set up in the Western Territories, but modern seismologists, so modern people that study earthquakes, have estimated the quake's magnitude at about 7.6 on the Richter Scale, which I believe is scale. What was the energy released by the quake? I'm going to underline the question. We can figure out what we're trying to solve for. Solve for which variable? Which variable?
Yeah.
Okay, which means we should be given the other variable. There's only one other variable. There's only R, which is Richter scale. What am I going to substitute for my Richter scale number? 7.6. Good. Equals 2/3. That log doesn't have a base because it's common log. 0.37e, which means it's a base 10 plus 1.46. All right, this is a log equation, which means I know I'm going to need to use an exponent eventually. Okay? But before I can use an exponent, I have to isolate the log part of this. So I need to isolate this part of it before I can use an exponent, which means I have two numbers I need to cancel. What should I cancel first? So we're going to subtract 1.46. Good job. 7.6 minus 1.46, 6.14. Bless you. Okay. One more number I got to cancel. How do I cancel 2/3? Divide by 2/3 or multiply by 3/2, which is like multiplying by 1.5. Okay. 3/2 times 6.14, 9.21. All right. We have officially canceled everything and the log is isolated. Now that the log is isolated, we can cancel the word log using. No, can't cancel a log using natural log. Base 10, a big base 10. Yep. Because a log has a little base of 10, which means to cancel it, we need to use a big base of 10. Big base 10, big base 10. So on the right-hand side, 10 to the power log base 10 will cancel. On the left side, we'll have 10 to the power of 9.21 equals 0.37 E. Okay, and then we have one last step to get E, the energy by itself. What is that? Divide. And this is one I want to put in my calculator so I can actually see what that equals in kilowatt hours. A big number. All right, 10 to the power 9.21 is, okay, and then I need to divide it by 0.37. Yeah, big number. Hold on. We're in the 4 billions. 4 billion. 383,270,533 kilowatt hours. That's what energy was measured.